Hello, welcome to Lab 5, the energy and motion of a bouncing basketball. The objective of the lab was to analyze the change in kinetic, potential, and the internal energies of a bouncing basketball with some initial velocity. The result was a computational model approximately followed the data from the tracker video, and some possible errors included the drag force and the effects from collision. Another result was that the energy principle was satisfied. Some physics principles that you need to know are Newton's second law, which was used to predict the motion of the bouncing basketball, and the energy principle, which is used to calculate the change in kinetic energy, the change in potential energy, and the change in internal energy. Some energy equations that were used in the code were the kinetic energy equals 1/2 mv squared, gravitational potential energy equals mgh, and the change in internal energy equals negative change in kinetic energy minus the change in gravitational potential energy. Here is the video from Tracker. As you can see, the origin is placed at where the ball is dropped, and the known height is going to be the distance between the lock mechanism on the door and the door handle. And I track the center of mass for the ball throughout its motion. I received the data from Tracker from this grid and imported to a CSV file, which I later imported into my code. Here is my code. First thing I changed was the ball's mass, as well as its position and its velocity, which were used and calculated from Tracker. Next, I changed delta t to a small value, and I initialized g and j hat. I also calculated the kinetic energy and the gravitational potential energy, and I read in the CSV file from Tracker. Here is my first while loop. This first while loop is set to a time from right before the ball dropped and hit the ground. I calculated the initial kinetic energy and initial gravitational potential energy. I found that the only force was gravity, and I calculated that. I updated the position of the ball, as well as updated the energy of the ball, such as the kinetic energy, the change in kinetic energy, potential energy, the change in potential energy, and the total energy. And I graphed that as well. Here is right after the first while loop. I calculated the velocity of the ball right after the bounce, as well as the new kinetic energy and the new gravitational potential energy. Here's my second while loop, which had a timer that stopped right before the ball reached the new height. And I followed the same steps as in the first while loop. Here is right after the second while loop. I calculated the change in gravitational potential energy, the change in kinetic energy, and the change in internal energy. And I also had a print statement, which we'll talk about later. Here is my code when it's ran. As you can see, the blue ball is the experimental and the red ball is the actual computational model. And these two graphs are a result of my code, which we will talk about soon. Here is the print statement that I referred to. I was able to find the kinetic energies, the change of those kinetic energies, the potential energy, the change in potential energy, and the internal energy. As you can see, the change in kinetic energy decreased, and the change in potential gravitational energy increased, but there's still some discrepancy. There is about a 0.001 joules difference that is lost, and that is the change in internal energy, which we will talk about later. So the energy principle is not broken as well because there's an internal energy, and energy is not lost. Here's a position graph. Initially, the computational model and the experimental model followed each other well, but after the bounce, which is right here, there was a discrepancy. This could be due to drag force, which is not accounted for on the computational model, as well as the collision, effects of collision. Here's the energy graph. The change in kinetic energy is in blue, the change in potential energy is in red, and the total energy is in green, which is 0. So what does it mean? Is the energy principle satisfied? Yes, energy is conserved because the total energy is equal to 0 once all the components are graphed, as shown in this graph which we previously talked about. What does it mean, question number 2? What energies constitute the internal energy? There is a rotational kinetic energy. That is, the basketball rotates and spins while in motion. And this rotational kinetic energy could account for the 0.001 joules that were not accounted for in the kinetic and potential energy differences. And to prove this, we'll look at this video once again. As you can see, the ball rotates a little just while in motion, and that could be the resultant of the change in internal energies. Thank you for watching my video, and I hope you learned something new.